it can be quite hard to plan the room that all the off-grid equipment goes in. It takes up a lot more space than a just standard batteryless solar array, which may not require any space at all. It's very common. What I commonly do is put my solar on the roof, run into the attic, and then I put the inverter outside on the north side of the building, on the shady side of the building, and then just come out the soffit and land on the inverter outside. Now, is it better to have the inverter inside in a air-conditioned space? Yes, it is. But as a solar installer, if I have a service call, it's convenient to have the equipment on the outside of the building. And a lot of the high-quality batteryless solar inverters that are intended for the American market will have temperature ratings and environmental ratings that allow them to be located outside. That's not always true with battery inverters. Battery inverters many of them are not rated for outdoor, and some are, and generally they're more expensive. No surprise there. Electrical space has to be dedicated. So you cannot share HVAC or plumbing or other kinds of scope with your dedicated electrical space. So now this is the inside of Half Moon's control room. And actually, this is more or less a code compliant room. The one thing that is not really compliant here is just using this area for storage. It has to be accessible. And then even though this air conditioning duct is here, it's a 6.5-foot tall dedicated space. So just imagine you draw a rectangle around your dedicated electrical equipment, and just imagine that none of your other stuff can be inside that space. Now, some of the planning that trips people up is the space has to be ventilated. Your unsealed flooded lead acid produces gas when it's being charged, and that gas is explosive. It's also light. It will go to the top of the room. So what's common is to ventilate the room. Now, according to National Electric Code, a air-conditioned space with an air handling system is a ventilated space. But there are more robust requirements. This is one area where International Building Code is actually a little bit more stringent than National Electric Code, where they require the batteries to be continuously vented. And so at that point, the common strategy is to put a hood over the batteries and have like a computer fan that is always on, venting that gas to the outside of the building. So just like having a plan to get that air that's going to rise out of the battery banks to capture it and shuttle it to the outside is a requirement. And that would only be for unsealed batteries. For sealed batteries, they don't emit the gas like lithium-ion batteries, so you don't have that ventilation requirement. So here's the what they say is ventilation shall be designed to limit the concentration of the hydrogen gas to be 1% of the volume of the room, and that continuous ventilation shall be provided at not less than 1 cubic meter per square foot of floor area. And so the way that they get around having very robust ventilation requirements is putting the batteries in a dedicated cabinet and only having that cabinet vent to the outside so that you don't have to have continuous air handling for the entire room. This is the International Building Code. National Electric Code just has something that's more akin to item number 1, where the ventilation shall be designed not to concentrate the gas to 1% of the total volume of the room. How you would calculate that, I really haven't a clue. When I'm planning my rooms, we're basically passively venting the air out the top of the battery box by sloping the top of the box and leaving a vent at the top of the box, or putting fans in a hood and having an inline fan in the coming out of the pipe that comes out of the top of the hood to the outside. Um, your battery room has certain rules, like the most important one is to prevent unauthorized access to the room. Your battery terminals are hot, and they may be given a little bit of physical protection. But I had a client who was kind of weirded out that he could just walk into. In this case, we had a shed for the batteries, and I think he was planning on using his shed for more than just his energy system. And he's like, well, wait a minute, I could just walk in and open up the batteries and stick my hand in and get electrocuted. And it's like, well, yeah, that's why you need to lock that storage shed and make sure your kids can't look around and get into it. Um, Spill control for your free flowing electrolyte. So that's for when your batteries start to get large. But what that's talking about is if you overflow your batteries, if you put too much water in them and then you subject them to a high charge, like a conditioning charge, the gas can cause the electrolyte to bubble out the top of the battery and spill onto the floor. So it's important not to overfill your batteries, and the battery watering kits will prevent you from doing that. They basically have little floats inside the caps that close when the water in the battery gets full. So here's the National Electric Code requirement that refers you to National Fire Code that gives you the either or option, whereas the International Code is both. So I imagine National Electric Code will eventually get more strict and require continuous venting at in the future. And then there's additional rules for special cases such as schools, educational facilities, where buildings where there are people on a continuous basis who might have be in closed conditions 24/7 or have special needs or still are in a state of physical development. Um, let's see. So, batteries are rated to handle elevated temperatures, even though they're rated to handle, even batteries can handle, freezing temperatures without freezing. It's like kind of like salt water doesn't freeze when fresh water freezes. Your batteries, it takes getting down to, closer to like below 8 degrees Fahrenheit for batteries to start to freeze. And at the same time, batteries can take higher elevated temperatures, although you'll get better performance out of your batteries if you do keep them in a conditioned space. So, when we're thinking about that stranded electricity that always will occur on a well-sized solar system, you might want to think about, well, maybe I could put a small air conditioner inside of my battery box to only run when the battery's at a full state of charge and keep that battery life healthy. It's not necessary and it is superfluous, but the best thing to do with stranded electricity is to put it to superfluous use, and maybe running a dehumidifier. And if you're in a humid environment, you're going to need distilled water to put inside these unsealed batteries. So maybe you use that stranded electricity to generate distilled water right on site and feed it into a tank, so that you're not having to go and buy distilled water to put in your batteries. A typical home is going to go through maybe a half a gallon of distilled water a day on a regular sized house running off of flooded lead acid batteries. So that's during peak times when you're watering your batteries once a week in the summertime. You're going to be adding 3 or 4 gallons of water for about a 60 kilowatt hour flooded lead acid battery bank. And another thing to keep in mind is that even though your inverters are often rated for higher elevated temperatures, they do undergo efficiency loss at elevated temperatures. And furthermore, inverters produce heat, so you take your ambient temperature outside, the internal temperature of that battery inverter is going to be even higher than that. And so for those reasons, having your battery inverter and your batteries in an air-conditioned space is a good idea if if your site and budget allow for it. And we're talking about larger systems rather than those small off-grid systems you see on off-grid living shows on television. And so what these charts essentially state is that your batteries will degrade at elevated temperatures. And it's actually kind of interesting. The battery capacity will slightly increase at higher temperatures. So even though they'll degrade, they'll also store a little bit more power. The colder the battery gets, eventually, what we're seeing here is like at minus 20, it starts to freeze at a 50% state of charge. So we're still talking about being able to get the temperature of batteries to be below freezing. It's only if you're up in the northern half of the United States, where outside in the dead of winter, it can get down into negative digits, where you have to think about, heating the battery so that it doesn't break. Whereas what you'd otherwise have with a cold battery is simply reduced storage capacity. So again, having a heating element inside your battery box that in the winter time runs during periods when the battery is at a full state of charge is not a bad idea. Just to kind of fine tune your battery box with a little bit of temperature regulation. So I put these two pictures online because actually both of these pictures have electric code violations for space requirements. Now, often you'll put batteries in kind of a forgotten about space in the house, whether it be a utility room or a basement or some cavity inside, adjacent to the building foundation. And so it's tempting to, just kind of cram the batteries in there and not give a thought about the fact that this equipment does need to be accessible and serviceable. The National Electric Code requirements change based on, basically you need enough space to be able to stand in front of the equipment and work on it comfortably, and not leaning too far over to access it either. And so this 3.5 feet of working space in front of the equipment, it varies a little bit. what really changes is if there's a wall behind you or if there's other electrical equipment behind you, it might go up to 4 feet. If there's a wall behind you, it's 3.5 feet. Um, the width of the working space is actually pretty flexible. You need to have at least 30 inches wide of space, and that's really only gonna come into play when you have electrical equipment that is narrower than 30 inches wide, and it can be that 30 inches can be on either side of the equipment. It doesn't, so you can go have a wall, and then as long as up from the wall you have 30 inches of dedicated electrical space, then you could run your gas line alongside there. The height, we mentioned that 6.5 foot requirement, so your air conditioning duct would have to be 6.5 feet tall, and lo and behold, in Half Moon's control room, their air conditioning duct is 6.5 feet up from the top of the floor. The requirement that kind of gets overlooked the most is the depth of working space, not the depth that I need to stand in front of the equipment to work on it, but how far out. If you're landing a piece of equipment on the wall and another piece of equipment on the same wall underneath it, so if I'm just standing here kind of looking at the wall here, and I have a piece of equipment here, and a piece of equipment here. What we're talking about when we say the equipment shall not extend more than 6 inches, we're talking about more than 6 inches from each other. So, one piece of equipment cannot stick out more than 6 inches from the other piece of equipment. And so where that comes into play here, we're going to go back to some pictures, but the batteries are generally 2.5 feet long, and your charge controllers and inverters are generally only about 8 inches deep. And so what we see in this picture here is that our batteries are sticking out a couple feet from the wall, and then we have this service panel where all our breakers are. That definitely is a piece of equipment that would need to be accessible and worked in, and you would have to lean more than 6 inches over the battery bank in order to get into this box. So, that's where that would be a code violation, which is kind of funny because these are pictures taken from the battery manufacturer's website. Likewise, you would need 3.5 feet, and this is electrical equipment, but then there's a physical barrier here. This would have to be 3.5 feet from this piece of inverter equipment so that you could actually stand in front of the equipment and work on it. And so when we were planning the layout for our off-grid house, initially we were thinking that we could just put all of our equipment along this side of the wall. But what we realized is by the time we got our double-stacked inverters and our electric service panel where everything's tied in, and our charge controllers that plug into the solar array, our electrical equipment is now overhanging our batteries, or vice versa. The batteries are protruding out by more than 6 inches with electrical equipment mounted above it. So we would have to go with kind of a catty-cornered configuration. Except if you're really following along and paying attention, you could say, okay, but didn't I have to add water to these cells and service them? And the answer is yeah, you do. And so actually, even butting up the battery against the wall like this is a code violation, because you would have to lean all the way over the battery bank to get access to these back cells. Now, in our case, this is inside a garage, and so we could cut a window here to gain access to the other side of the battery bank. But if you're in a room, just a dedicated room with four walls and nothing funky going on, and you're installing a flooded lead acid battery bank, the most space efficient layout for the battery is to take this short edge of the battery and just kind of put it, just imagine this, there's nothing here in this layout. You would have to be 3.5 feet from the wall, and then you would put that short end of the battery bank along the wall and stick the battery out from the wall so that the short end goes along the wall and the long end comes out from the wall. And that way you could walk all the way around the battery and service all the cells inside of it. And so I guess the moral or the lesson learned from that is when you're planning your battery room to be inside a room, then you would place the short end of the battery bank butt up against the wall rather than the long end of the battery butt up against the wall. And so really the smallest battery room, if you're just having a room just for the battery bank, would have to be 3.5 feet here, and then let's just go ahead and say that the batteries are 3 feet long, and then you'd have to have another 3.5 feet. And so at the bare minimum, your battery room is going to have to be at least 10 feet wide, and then have additional space, for your equipment, other equipment elsewhere. And so it's not a terrible idea just to build a battery box outside of the building for your equipment, where the batteries are inside the box and you have a lid and can just kind of get down into the batteries that way. But keep in mind that you still cannot put that battery box butt up against the wall of the home. You would still have to have 3.5 feet of space to access the cells from at least those sides. So I guess if you're doing a battery bank and you want to butt it up against a wall, again, you would butt up the short end against the wall and have it stick out from the building rather than butt up the long end. So we talked about battery maintenance and hydrometers and taking the specific gravity. When the batteries are fully charged at a given temperature, and the batteries manufacturer will give you temperature correction factors, but it should always read the same specific gravity at the same state of charge at the same temperature. And if one of the cells reads a different specific gravity, well, that's when the battery's kind of nearing the end of its life, or perhaps needs a conditioning charge applied to it. So your equipment also starts to take up a lot of space. You might have two inverters. Well, for one, when we're doing solar, where you might get a 10 kilowatt solar array and undersize your inverter, and your inverter's 8 kilowatts. But to power a home, that home may need 15 kilowatts or 20 kilowatts, or even a very, 5,000 square foot home or larger, may even need kilowattage that's beyond that. And so you're not really just buying one 8 kilowatt inverter. If you need 20 kilowatts of capacity, you may be buying three inverters instead of one inverter, and those will take up 3 times as much space as one inverter. Additionally, the battery inverters being less popular than the non-battery inverters have not gone through the design iterations that the batteryless inverters have. So whereas batteryless inverters over the last 10 years in solar have gotten smaller and smaller and smaller, the battery inverters are still up at a large, heavy form factor. And of course, they have more stuff in them than a batteryless inverter. So, your battery inverters are large and heavy, and then you need an electric service panel that everything's tied into. You might actually need two electric service panels. You may need a DC service panel for tying in your battery bank and your charge controllers and the DC side of your inverter. You may need a separate AC service panel for the output of the inverters before to parallel them together before going into your main service panel for the home. And so then we get into our charge controllers as well. And remember, charge controllers kind of do the same thing as inverters do. They take the solar power and then they convert it into something that's useful for the rest of the system. And so in this case, we have, these are all, 5 kilowatt charge controllers. And if our array is 20 kilowatts, we would need, 4 charge controllers and then 2 inverters to give us enough power for the house, and then our service panel. And so the takeaway is we're not just talking about one inverter that kind of hangs on the side of the building like a batteryless solar array. The battery room to house all of this equipment, needs to be at least 10 feet wide for the batteries, and then maybe it needs to be 15 feet long at minimum to have enough space for the flooded lead acid batteries plus all of your electrical equipment. So we're talking about a bare minimum of maybe 150 square feet of space for your battery and inverter electronics that's dedicated. And so it can be kind of hard to convert a water softener closet is not enough space for an off-grid battery setup. And so just to kind of get an idea of the dimensions of these batteries, I would say a well-sized battery bank for an off-grid residential home, we're talking about the average residential home, not a 5,000 square foot home, not a one-room cabin out in the woods, but we're just talking about your typical, 2-story, energy efficient, maybe a 4-bedroom, 2-bathroom house would be about 122 kilowatt hours of storage. A volt times an amp is a watt. So, and these are 12 volts. So 12 times 12 is about 14 kilowatt hours. And so we need about 8 of this particular battery. Or maybe we could get away with less. If we're going for 122 kilowatt hours, we'd say, okay, well, divide that by 48 volts, and then we get how many amp hours we need. Let's just pull that up. And so if we're looking for a 122 kilowatt hour battery bank and we're dividing it by 48 volts, what we need is, so kilowatt hours to watt hours or whatnot, we need about 2,540 amp hours. And so I would put that on 2 battery circuits, and that's because our one battery circuit only goes up to 1,690 amp hours. And so we need to divide that by 2. Now we got 1,270. And so here we go. This is the battery we want to have 2 circuits of batteries all the way up to 48 kilowatt hours. Of space. And so these batteries are 38 inches. These batteries are 38 inches long by 10 inches wide by 25 inches tall. And so if we have 8 of these batteries, and they're 10 inches wide, and we're stacking them all right next to each other. Just the battery bank alone is going to take up almost 8 feet of floor space. And then you would need, if you have electrical equipment on both sides, you would need 4 feet of space to walk around. And so if your battery's on one side, let's say you have a perfectly rectangular room. You want to see what's the smallest room for my batteries plus my service equipment. You'd say, okay, well, I have a rectangular room. And so we know the batteries are going to be 36 inches or 38 inches long. So let's just call it 3 feet. And so we have 3 feet of space for our battery and then 3.5 feet of space on both sides. That gets us to 10 feet. And then we say, okay, well, on the other side of the room, we got all of our equipment, and we just looked at our 4 charge controllers and our service panel and our 2 inverters, and that was about 10 feet of space. And our batteries are sticking out from the wall about 8 feet. And then, not because we have a wall here, but because we have electrical equipment on both sides, we need 4 feet of space here, and then plus 1 foot of space for our equipment. And so what we're looking at as like the minimum space for a typical off-grid battery room would be, at least 10 feet by 15 feet. So 150 square foot of floor space just for a code compliant basic off-grid setup for your average home. And that would be without any room for expansion. And so I haven't actually built one of these yet, but kind of how I would do it on my own, if I had a house and I didn't have, 150 square feet of empty space inside the house or the garage to build a battery room, if this is the side of the house here, what I would do is stay, 3.5 feet from the edge of the building, and then I would just build a box and put the, inverters and service panel on one side of the box and the charge controllers and maybe the DC panel on the other side of the box, and then have the batteries in between. And then at that point, that box might only be, 4 feet wide by, perhaps 10 feet long. So, if you have a battery box that's outside of the house, it's actually might be able to be a little bit more space efficient than fully enclosing that inside a larger room if you're space constrained. Now, if you have the budget, putting it inside the room in an air-conditioned, ventilated, temperature-regulated space will get you better performance out of your system. All right. We're going to revisit racking because this is kind of an advanced class, and I wanted to just briefly talk about some advanced racking considerations that we really don't get as far into in our other solar programs. You can go to your online solar racking manufacturer websites, and they'll have design tools available for you to specify your system material. I like installing solar where my local jurisdictions allow it, all the way to the edge of the roof. I think that when you cover the entire roof with solar, it's better for the roof life, so you don't get uneven aging across that roof surface. What degrades shingles the most is direct exposure to sunlight. And so, the south side of your roof should age more quickly than the north side of your roof because of that. So, covering the south side of your roof, and by south, I mean anything south. And as we talk in our solar class, you might also want to consider going on to the north side of your roof as well because of economies of scale. But anyway, the point I'm trying to make is, regardless of where the array is located, the corners of the array are going to experience the greatest wind loading. And so what I will do with my designs is, let's say I'm using a 4-foot on center layout and I'm staggering my attachments so that I'm evenly distributing the load across all of the rafters of the rooftop. I will then, even though I have this staggered layout here, I will then go and add additional attachments at the corners of the array to give it a little bit more structural reinforcement right at the corners to counteract that high wind load. And then if you're in an area where you get heavy snow, instead of going with the 4-foot spacing on center, or depending on the design, you might even go with a 6-foot on center spacing. What I will do is I'll start out around the perimeter of the array with a 4-foot spacing, and then if the array is large enough, and I'm still staggering my L feet, so you can't do this just with one row of modules, but if I have multiple rows of modules, in the interior section of the array, I might widen out my spacing to 6 foot on center, provided that I can still hit every single rafter going across the rooftop. But if you're in an area where there's heavy snow, another thing you want to do is take the bottom row of rail and stick to a 2-foot on center spacing. The reason being is that snow load is going to be the greatest at the bottom of the array when the weight of the snow kind of pushes down onto the bottom attachment points. And so I have heard of a couple of instances up in the very northern United States where heavy snow on the roof actually causes the solar array to crush through the roof decking, and that can be avoided by more attachment points to better distribute that weight across the truss of the roof. Another thing to look at that I can think about is rainwater runoff on our array layouts. This was a design that I got from a developer, and what stood out to me, I had never seen designers consider rainwater runoff with their array layout. But here in this design, they're specking out the worst tributary area, kind of assuming that all the rain from the panels is going to cascade down onto this bottom section. And that started to get me thinking a little bit more about my designs, where I used to say you want to put your modules all the way up at the top of the roof so that you don't get snow mounding up at the top of the array. Now, you do need to leave about 3 feet from the top anyway, which is a good idea for a variety of reasons. One, staying off 3 feet from the top is going to reduce your wind loading, which is high at the top of the roof. Two, you don't want to completely close off that roof cap. You want to, if there's something that goes wrong with that ridge vent along the top of your home or your roof, you want to make sure that it's accessible and repairable. So for a variety of reasons, staying at least 3 feet off the top of the roof is a good idea. But now I'm thinking about things like, well, what happens when all of this rain comes off of the module and then just hits these shingles? So now you're going to get a lot of shingle degradation right down at the bottom edge of the array. And so what's really best is to start your array, kind of right at the bottom of the roof line, or maybe offset by an inch or two, so that that rainwater can come off the module and then go right into the gutter and not overshoot the gutter, but also not degrade the shingles along the roof line. And so, I used to just start my arrays 3 feet from the top of the roof. And now, I'll start them, an inch or so from the bottom of the roof and then tile them up until I get to the point where I can't go any further to maintain that 3 feet from the top spacing. And then when I try and do my designs, I try and cover, the entire roof rather than just a section. One thing that we did, ultimately with this particular roof is we went and we looked at the site evaluation of the roof, and it turned out that there was attic space in this lower section, but this upper section was exposed, kind of like an open air cabin on the inside. And so we didn't want to go up onto that top section of the roof. We didn't want our lag screws to be like sticking through into their living room. And then we also reduced the rainwater accumulation by spreading the array out. And as you can see, we just kept it off of this line to not be shaded by these dormers. So this was a design where the budget did not allow for doing the whole roof, and this is kind of how we tweaked the design to make it a little bit better, more aesthetically pleasing, and a little bit better for the roof as well. And it kind of looks like the roof is smiling, so there's that too. I think that when you're planning your solar design, aesthetics are very important. A solar module that is 290 watts today, efficiency is always improving. So next year, the value range modules won't be 290 watts, they'll be 300. And maybe 2 or 3 years from now, the value range modules might be 350 watts, whereas 350 is kind of on the high end. There's even a 400 watt module within the same surface area for the very high end. I usually don't go with the ultra premium top shelf modules because they cost over twice as much as the value range modules. And in Mississippi, we have to go for budget conscious. What I do when I'm to improve the looks is I specify all black solar panels, because as they say, black never goes out of style. And so it's, whether or not it's a 300 watt module or a 250 watt module, you can't really tell by looking at it. Furthermore, it's just a matter of having enough surface area to install. So it doesn't really matter if you go with 250 watts or 300 watts. They both get the job done. But I will go with a clean looking symmetrical array where all the wires are hidden underneath the array through an internal wire run. We're transitioning into the attic and then running back to our service panel using an all black residential solar panel to make it look good. And I feel like that is what is going to maintain the value of the home. When you're looking at real estate value and what adds value to the house, it's more about the curb appeal. And so when someone drives up to a house and they see solar on it, they don't know watts, they don't know their electric bill, they don't know production. They just think, oh, that's a solar house. It must have low electric bills. What we want them to do when they drive up to the house is say, oh, wow, that solar array looks really good. It improves the aesthetics of the house. We don't want them to say, wow, that's an ugly solar array. I want to take it off of the roof. And so those considerations don't really have anything to do with production and have very little to do with cost savings. And but we do see that has those issues are more strongly correlated with the resellability and what value the solar array adds to the home, rather than the more pedantic, oh, this is 10 kilowatts, so it'll produce 14,000 kilowatt hours at 8 cents a kilowatt hour over 20 years. So there's about $30,000 of cost savings to be had. So it's going to add $30,000 to the home. It would be great if that's how things were calculated, but that's not. So it's more to do with aesthetics, and so I would not ignore the value of aesthetics when planning your array layout. When choosing the racking, my favorite solar rack is, without getting into the manufacturer, because there's a couple of these out there. Some are more expensive than the others. I generally go for the less expensive one. But what I look for in my rack is the rack to have a very wide U channel. A lot of solar rail just has this very narrow channel at the top that's just barely big enough for the hex head of a bolt to slide down. What these U channels use is more like a rectangular bolt that's used with Unistrut, which is a wide U channel. And the rail might seem a little bit flimsier at first, but it's that it really gets a little bit more stiff when you start putting these rectangular metal plates across the top of it. The reason why I like this U channel is because it provides integrated cable management. Now, what the thinner rail does is they'll have a tiny little U channel for the hex head of a bolt, and then they'll still have a little channel for the bolt that attaches to the L foot, and then they'll have another little side channel that you're supposed to cram all your cable into, and somehow it magically stays in that side channel with tie wraps over a 20-25 year period without any critters coming around and chewing on the tie wraps, or the tie wraps just busting off with age and time and thermal expansion, etc. This is really a messy way to do cable management. What I like about the U channels is I can just lay my cables into that U channel, and it basically protects the cable from critters, from squirrels. Another option is putting netting around the array perimeter, which some quality solar installers do. But squirrels are pretty pernicious, so even if you put netting around the solar array, I don't trust that netting to hold up over the long term. And all it takes is one little breach for that squirrel to have a mansion to live in up on top of your rooftop. So I like the rail that has this little U channel. So we have a question: how do you deal with re-roofing, especially in hail and the U.S., where new roofs are common every time a storm rolls through? So that's a great question. I actually got started in solar in Austin, Texas. And Central Texas is the worst part in the country for hailstorms. And just one time we saw this mother of all hailstorms roll through. And it was biblical. It was crazy. It was you drive down the road and every single car in the parking lot is total. And it's not just the hood is damaged or the front windshield is smashed through. It's like the sunroofs, the back windshields. Anything glass shattered on every single car. So car dealerships, they're tearing their clothes in grief. Roofers are throwing parties because they know they have 2 years of work ahead of them, because every home in the neighborhood is getting a new roof because of this crazy hailstorm. Solar panels are rated to take 1-inch hail at about 60 miles an hour. And so they're stronger than your average roofing material. I'm not trying to say they're bulletproof. You know, you can't walk on a solar panel. It might not break, it might not shatter the glass, but it's not good for it. Um, but in this hailstorm, we had one service call out of about 20 customers. And out of that one service call, only two of about 20 panels were damaged. And so we basically just took two panels off and put two equivalent panels back on and went about our day. And so that's where I would say covering the whole section of the roof is important, because if you only cover a small section of your roof and the rest of the roof gets damaged, then you would either have to take the array off and put it back on again. And guess what? That's more expensive than just putting it on for the first time, because a lot of the hardware is not designed to be bolted and rebolted and bolted and rebolted. And then you have to figure out, if it's not your install, what the first installer was thinking. It can be an opportunity to fix some errors of the previous iteration of installs. Good roofers can weave shingles, starting with the top of the roof in strips going down to the bottom, but it's not a cheap or enjoyable process. And so that's, how I would deal with re-roofing with hail or wind, is I would adjust it in the design phase. And I'd say, that's why, if you don't have the budget to cover that entire roof section with solar, kind of wait until you do. And at that point, it's also a matter of design to say, well, if you're not going to cover up the entire roof, then you might want to leave all the way from the bottom of the roof all the way to the top exposed, so that roofing strip can be adjusted without taking the array off. Worst case scenario, you have to take the array off and put it back on again. So these little boxes are called DC optimizers. And while I don't agree with how most solar installers are reading the latest, iteration of National Electric Code, many in the industry are stating that you must have these little rooftop boxes behind essentially every single solar panel on the rooftop now for fire safety. I think they're misreading code. I don't think you have to use these things. I think it's a good idea to use these things. I mean, what these boxes were originally intended for is shade tolerance. So that what they do is they allow every panel to operate pretty much independently of each other. The Solar Edge system in particular is really neat, because what it'll do is it says, hey, this cable is rated for 600 volts. The operating voltage of an array is closer to 400 volts. And so what we're going to do is use our little voltage regulators, they call them DC optimizers, behind every single panel to step the voltage up to, 550 volts, right up to 600 volts. And if one panel gets shaded, it drops the amperage of the panel and ups the voltage of the circuit. Basically it mitigates the impact of inline shading. And so the optimizers are really useful for shade tolerance. They also give you more data on what's going on with your array, because you can pull them up online and see what every single panel is doing. And then they also have a fire safety purpose of isolating the power to the individual solar module, so that when the power goes out, the power is dead, not even right up at the rooftop, but right at the individual solar panels, such that the entire voltage of the system is you no longer have high voltage just hanging out on the top of the roof when there's a power outage. And that power outage that people are concerned about is if there's a power outage because your building's on fire and the firemen have cut power to the building, they're concerned about high voltage solar still being on the rooftop. And so by isolating it to the panel itself, you don't have the panels stacking up to that high, 600-volt design spec. The problem with these DC optimizers is now you have, normally you would have a solar panel and a solar panel, and they just kind of plug in to their next door neighbor. Well, now you have an optimizer, and the optimizer plugs into its next door neighbor, but you have to plug in the solar panel to the optimizer. So now you have, twice as much cable on the rooftop. And so your cable management becomes all the more important. And so what I do is I select this U-channel rail, and then I'll go ahead and build this thing down on the ground. I won't wait till I'm up on the roof, because the rooftop is a very uncomfortable place to be. So I'll build these rails down on the ground, and I'll go ahead and measure out and land my optimizers on the rail. And then I'll go ahead and, in addition to running my home run circuits through the rail, I'll also put my optimizer cables in that rail and then tie wrap them into the rail. And the reason I do that is because, normally you're using tie wraps or metal cable clips to do wire management, and neither are perfect. Tie wraps can break. Tie wraps can also cinch the wires, which become pinch points that eventually vibration in the system or thermal expansion in the system could start eating into your module cable, which is really not a huge deal. Solar module cable is very thick. It's much thicker it's like the same thickness as coaxial cable, except the copper inside is larger. So it's a very thick cable. The module cable clips are very good for tucking the modules out of sight and out of mind, but the problem with the cable clips is that your cables can pull out of them. And so neither tie wraps nor cable clips are perfect cable management solutions. And so what I'll do is I'll tie wrap into here, into the rail, but then once you start bolting the panel or clamping the panel down onto the rail, what happens is the module frame itself starts to overlay this rail. And so the module frame itself and the little clamp that goes, between the module frames is what permanently secures the cable into the rail. So I'm really just using tie wraps to pre-position the cable, and then once the modules go on, that is permanently securing those cables into the rail so that when I'm installing them, I know that they're never coming out and that they're also physically protected from harm, that it almost gives me the same protection as a netting that goes around the perimeter of the array, but I'm not having to pay for it. It's already there as part of the racking design. And so the only thing you have to manage at that point is the module whips that plug into the optimizer. And traditionally, you put the optimizer underneath the solar panel. And that gets a little tricky because you're trying to juggle putting the panel onto the rack and plugging in the panel to the optimizer. And at the same time, you get a bunch of slack from these panel whips, because the panel whips are intended to go all the way over here, or even in landscape, go all the way to the other side. So these whips are pretty large, and you get a bunch of slack. So you're trying to manage the slack and plug in the optimizers while bolting the panel right down on top of it. And so what I've discovered is what I do is, instead of putting the optimizer underneath the panel, I put the optimizer underneath the next panel over. And so what that allows me to do is twist these cables together to get rid of any slack. And it also lets me bolt the module onto the rail without having to deal with plugging in the optimizer. So, instead of having this like elaborate trapeze juggling act where if you don't stick it correctly, all this loose slack just falls onto the roof, which is not good. Not only is the cables touching the roof, subjecting it to higher temperature, it's also subjecting it to that abrasive shingle, and it's also something that a squirrel could look underneath and see the cable, and it's more attractive for them to nest and chew on. And so instead of doing that all at the same time, my step one is to bolt the panel onto the rail, and then step two, I just grab these module whips underneath and pull them out. And then step three is I twist them together and plug them in. And what that achieves is there's no slack. Most of my cable is already tucked into that rail. The module frames are securing the cables into the rail, so they're not going to fall out. And I just kind of relay that process all the way down to the last module on the circuit, where I have two optimizers underneath the last panel, one from the next door neighbor, and then the last module on the circuit, at which point I go into my rooftop transition box or junction box to go into the roof. And what that allows you to do is basically just look underneath the solar array, and it's almost like all the cables vanish. I mean, you can barely see the optimizers and cable whips because all that slack is managed, and it's just like there's nothing underneath. And I think that that's really the sign of a quality solar installer, is to be able to look underneath a solar array and just not see anything. It's kind of difficult to do. You have to put a lot of thought into how you're going to do that. You can mount the rails in landscape. It's actually not quite as hard as I've pictured it here. Some will just use a little bit more rail to mount them in landscape. What I'm trying to illustrate here is that the purlins, if you have purlins, that can kind of mess up your design a little bit and force you into a landscape configuration. And even so, with purlins, it's kind of hard to match up to get the right rail spacing with purlins. I guess another thing that I'm trying to illustrate here is that there's such thing as a shared rail system. And I would caution you against shared rail systems because they're very tedious to install. You have to be a lot more exact with a shared rail than when instead of having the shared middle rail, you have two. You just add an extra rail. Just some thought on shared rail. What's interesting to me about shared rail is that you can, if you were to, say, fashion your own flashing for this section, the shared rail section is completely waterproof. And so it's, using a shared rail system, it's possible to make just the roof out of solar panels and not have any decking underneath it. which would make a very interesting garage at the very least to build the roof out of regular solar panels instead of using like Tesla solar shingles. Another project that we would like to do, but we have not done yet, is to add an additional U-channel rail here and plumb it and run a heat exchanger underneath the array to take some of the heat from the array and use it for home heat and hot water heating. But I just have not had the risk tolerance to take that on yet. So on traditional racking systems, they're flashed. You're putting the flashing underneath the shingles. So you're getting up on the rooftop and either banging the roof with a rubber mallet to figure out where the rafters are, or using a high-end stud finder. Not your $40 stud finder you get at Home Depot, but like, a stud finder that costs $500 used that can see 4 inches into the rooftop, or getting into the attic and measuring out the stud spacing. What I will do typically, I haven't bought the expensive stud finder yet. So what I'll do is I'll use the rubber mallet method, and I'll take a white paint pen, and I'll go in and into the attic and measure out my rafter spacing. And then I'll take a rubber mallet and I'll start banging across the roof and just jabbing a little white paint mark wherever I think there's a rafter. And then I'll go down a ways and do the same thing without looking at where my previous marks were. And then I'll have what I think is a rafter, and then I'll have a couple of rows of that, and I'll be able to start to see where the rafters actually are. What were my false positives versus my true rafters. At that point, you pop your chalk lines and you drill little pilot holes. And once you drill that pilot hole, you're going to know if you're in the rafter or not. And if you miss, you stick a wire down that pilot hole and give it a twist, and you can kind of feel how far off you are from the rafter or not. And then hopefully you don't have to drill more than one other hole to get there. But even if you miss your hole, you'll go and caulk it and then put your flashing around it. So it's not that big of a deal, provided that you're doing everything else correctly. And so you have your little flashed attachment points that your lag bolts go through. And then it has a little slot that then gets bolted into your racking. No big deal. There's systems for standing seam metal. And I even recently found out that there are conduit supports for standing seam metal, which has always been an issue for me on what I do with my conduit. Sometimes with standing seam new construction, I'll run a stick of conduit up the roof and go into the roof cap before bringing my wire run down. And so it's like, well, how do you support that conduit there? Well, the same company that is the market leader for standing seam metal roof solar roof attachments now makes conduit supports for standing seam metal roofs. I actually like regular metal roofs better than standing seam metal roofs. And the reason is standing seam metal roofs are not designed to have solar on top of them. I mean, what happens is the attachments are strong enough to keep the solar array on the roof, but the metal roofing panel itself is not designed for the additional load that the solar array will have. And so what you read through the standing seam metal roofing manuals, and they will tell you that you got to put a clip on every single seam. And so that what that does is it makes even though you're not using rail, across the roof. It's a railless system, but at the same time, it costs the same, if not a little bit more, because you're buying so many additional clips to do it right. And then when you're not using rail, you have to be all the more square because usually, you put your attachments on, you put the rail on, and then you square the rail to keep your array square. Well, if you don't have that square rail, then all of your attachment points have to be dead on center. Why I like regular metal roofs instead is that the roofing attachments just screw into the roof. And you could say, okay, well, that's kind of scary to poke holes in a roof or to poke holes in a metal roof. Well, there's a lot of things that poke holes in a roof. Your chimney pokes a hole in the roof. Your top of the roof pokes a hole in the roof. There's attic vents, and on commercial buildings they have flat roofs with big giant holes for their air conditioners. So poking holes in roofs is something that roofers do as a normal course of business. And these for like a rolled metal or corrugated metal, they have very waterproof butyl tape that goes around the penetration and seals it right up. And it's a very easy process. And then you're actually going through the metal roof and into the rafter, which is a much more solid connection than just clipping onto the roof and not going into the rafter, which means you need more attachment points. Likewise for doing your roof penetrations, the best way to do it is to get a specialty transition box that's flashed. And so here's the hole that goes into the attic. Or you get a pipe boot and stub up some EMT conduit through it and have a flashed pipe boot, just like your plumbing vents on the rooftop. The reason why it's better to use the specialty box is because sometimes with your pipe boot and your pipe, you start to get too far off of the roof to tuck it underneath the solar array. And so it becomes a little unsightly when you can't hide it underneath the solar array. Most of your junction boxes are going to be at least 4 inches deep, if not 6. Most of your solar is going to be only about 4.5 inches up off the roof. And so, just trying to put together a solution from Home Depot becomes very difficult. Whereas these specialty transition boxes are low profile and can fit underneath the array, which is code compliant. Now, as far as the internal wire run, that's something where solar installers get a little tripped up on because they're like, why would I want to poke a hole in the roof? That could cause a leak. Well, generally that means they don't have a lot of roofing experience. They don't want to poke a hole in the roof. But I'll tell you what really damages a roof is not poking a hole in the roof and then flashing it and sealing it. And furthermore, they're going to be poking a lot of holes in the roof for their attachment points, so they better know how to flash and seal things to begin with. What really damages a roof is tromping around on the roof and spending an excessive amount of time with the install, which is another reason why we do as much as we can down on the ground before moving up to the rooftop. Because when you're stepping on those shingles, grit is coming off of the shingles, and that's damaging the shingles. Now, presumably you're putting solar on top of those shingles, and so while you're damaging them a little bit during the install, you're protecting them for the rest of the life of that roof. But when you're running conduit across the roof and it's coming out of the array and then dipping over the edge of your house and then running around the outside of the house, one, it's a trip hazard on the roof. 2, aesthetics, it doesn't look very good. 3, it's the hottest part on the building, and so you get into thermal expansion issues. And you also, it's wet, and so you get into water ingress issues. I mean, there's just all sorts of reasons to say that you don't want to run conduit across a rooftop if you can avoid it. That said, bending EMT conduit in an attic is not very enjoyable and sometimes very difficult, if not impossible. And so what I use instead is a cable that's called metal clad cable. So it is MC cable is how it's referred to in National Electric Code. MC cable or metal clad cable. And you got to use metal clad cable because DC is required to be inside of metal conduit. I will select a metal clad cable that has wet rated conductors inside of it. In very limited circumstances, and this is only in like your most heavily regulated environments. So this might be in like New York City, where you got a bunch of skyscrapers and multi-story buildings, and so they up the physical protection of electrical cables even further because they're concerned about, the multi-story apartment complex burning down. So they say we're gonna, metal clad cable this jacket. It provides some protection, but it's certainly not enough protection to prevent you from driving a nail or a screw through it on accident. And this metal DC conductors inside of metal has nothing to do with grounding. It's just for physical protection. Now, we talk about this in our code class, why AC power lines do not need to have this physical protection, but DC does. I think is a little bit of a case of solar discrimination and National Electric Code. But regardless, that's the requirement. Their DC conductors have to be in metal. I have not seen that in code be applied to your battery conductors, but it only makes sense that if your solar conductors have to be in metal inside the building, that your battery conductors have to be in metal inside the building as well. I'd say that's more of an oversight in code rather than something that's more reasoned. If you have a battery box that's outside the building, you don't have to be in metal. But I like this MC cable because the cables come pre-bundled into it and it's flexible. And so basically you just pull it through the attic and then strap it along the truss, and it's very easy to run and pull. And, while it is expensive, if you are on this side of the roof with your solar array, on the south side of the roof, and then on the north side of the roof is where your inverter is going to be, or the north side wall is where your inverters are going to be. If you go into the attic, your MC cable run is quite short. Otherwise, if you want to go in conduit, you run your conduit down to the side of the building, and then you go up the roof and down the roof, kind of under the eave, and then back around and then down. And so, that's expensive too. It's a lot easier to run metal clad cable through the attic. The only the downside of metal clad cable is that it's only rated for damp conditions rather than wet conditions. And so damp is an outdoor area that is still sheltered. So like a covered porch or a covered garage is a damp location. A wet location is a location that's subject to rain. And so what I'll commonly do is, if here's our roof of our house, what I'll commonly do is I'll mount the inverter on the wall, and then I'll stub up some EMT and then put a transition box right here underneath the eave. and then I'll be, coming through the attic with my MC cable, and then just come out the soffit with about 1 foot of MC cable. And so that if the inspector says anything about it, I look at that and I say, look, it's protected by the eave. And then, furthermore, we have a little bit of a drift loop area so that water can't get into the inverter. And that, at least in Mississippi, is good enough to say, maybe up here would be a damp location, but any further down would be a wet location. You also need to run a ground up to the rooftop, and the smallest ground that you can use for residential is number 8. And so for that reason, I will select number 6 MC cable because the ground is undersized, and so I can use the ground as my number 8 cable for the ground. And so what I'll often do in the attic is I'll put a transition box and I'll run my solar cables through the roof into the transition box, and then I'll transition into MC cable here. Sometimes I pull the MC cable all the way up to the roof and have my transition box be on the roof. And then I'll go MC cable through the attic, land on another transition box, and then just strip off the MC cable and then use the remaining conductor line and EMT conduit to land on my inverter. With your MC cable, you can get it with 3 wires in it, as pictured. You can also get it with 5 wires in it. And so you can get 4 number 6 conductors plus your ground, and that would cover 2 of your solar edge circuits. And because solar edge will up the voltage and drop the amperage of your panels, you can fit more solar panels along the same circuit versus if you weren't controlling that. And so, for many homes, all you need is 2 solar edge circuits, or sometimes 3. And so I would get, 1 4-conductor MC cable and another 2-conductor MC cable, just depending on the design. And at that point, how you transition from your MC cable to the rooftop becomes a little bit more of a technical knowledge. You have to know the right couplings and fittings to be able to do it in a code compliant manner. But they're out there. A good electrician should be able to piece this together. And so the takeaway is we can do a lot of pre-assembly in solar. The MC cable is pre-assembled. The racking we build on the ground. Our cable management we give thought and consideration to. And all of this will reduce the amount of time on site and reduce the amount of time on the roof. Ground mounting. I recently did a ground mount where we didn't use any concrete. And the reason was it was an off-grid site and the road was really bad. Really bad. It freaking bent the axle on my car bad. And I didn't want to have to deal with getting a concrete truck out to site and then being able to get it to where the solar array was going to be. And so what we used are called helical piles instead. I was in, like a sandy clay loam. If I was in rockier soil, I would use, instead of a helical pile, I would use what is properly called a ground screw. These are both referred to as ground screws, but this is a helical pile, this is a ground screw. So these were kind of interesting. They install with an upgraded Bobcat. I wouldn't say that it saved any money because they're more expensive than just buying the pipe and putting it into augering out the hole in the ground and pouring in your concrete. So I'd say it cost about the same, but it did simplify the job site. And my jury's still out on whether or not it's more cost effective, but I don't think it's any less cost effective than augering out and buying a bunch of concrete, pouring it into the ground. And some environmentalists are concerned about the environmental impact of concrete, and these are, just as good as concrete. There's a couple of different kinds of racking to consider for ground mounting. The most common kind, and the kind that I would recommend, especially to do-it-yourselfers, is a scaffold style ground mount where you have 2 rows of pipe with some reinforcement in between. That's cheap and easy, which is usually good. What we use to level our helical piles is a laser. This helical pile company is suggesting using a string and a bandsaw to level them. The laser, I guess, is more expensive, but it worked really well. And so you can install some ground mounts on uneven terrain. You just have to have a strategy in place to level out your foundations or the tops of your posts. Utility scale racking is a little bit different than scaffold style racking in that you don't have 2 rows of posts. Instead, you just have 1 row of posts. And the major difference between these is when you have 2 rows of posts, your foundations only have to go about 5 feet deep. When you're using 1 row of posts, they're typically going maybe 6.5 or 7 feet deep, which is just a little bit deeper than what a bobcat with an extension bit is capable of. Which really means that if you're doing a single post system, you're either going to have to use like sonotubes and extend your concrete a little bit out of the ground to still be within spec, or you use a pile driver, which is not really a residential piece of equipment. Now, the reason why single posts are so much better is because you can actually get, like a lawnmower underneath here and do some, it's a lot easier to do maintenance rather than, when you're impeded by, that extra post and whatever reinforcement is between your bleachers. So, your single post system is easier from a maintenance perspective, and a little bit more cost effective, a little bit fewer foundations. Now, tracking is kind of interesting because on a tracking array, you typically have just 1 row of panels along a single post. Whereas with fixed arrays along a single post, you have 2 panels. And so to me, that's interesting about tracking is that the foundations, instead of being 7 or 8 feet deep, you're back into shallower foundations, 5 foot deep foundations. And actually, tracking does not add that much cost to a project. Utility scale is predominantly tracking as opposed to fixed. And the utility scale market would not do tracking if it was not cost effective to do so. And so a lot of solar installers say, well, it's not cost effective to do tracking, but it's more that they're ignorant of tracking. Utility scale does not really do double axis tracking. It's more single axis where the panels track east to west. Now, there's certain terrains where, if you can't drive a big row of posts into the ground, if it's rocky terrains, and if you want to do above the ground concrete pours or something like that, then a fixed in place array is fine. Why don't we see residential tracking? Why do we see single axis tracking on utility scale sites, but we don't see single axis tracking on residential? Well, the main reason is that all of the residential single axis tracking companies 10 years ago are now the utility scale single axis tracking companies of today. And they're not interested in going back and serving the residential market. When you look at it from a cost perspective, really what's being added with tracking is a little rotating hinge at the top of the post. But whether it's a fixed in place array or a tracking array, you're still buying the post, you're still buying the cross beams, you're still buying the cable clips, you're still buying the panels. So, what you really need to buy is a actuator, a control board, and then these rotating hinges. And so the utility scale market says tracking's cost effective. Residential, they say it's not cost effective, but it's really due to a lack of access to tracking systems and a lack of manufacturing support, not necessarily that it's technically unfeasible. Technically, residential tracking should be cost effective in the same way that utility scale is. There's just no one serving the market. It's not a large enough market to attract attention. Another interesting thing they do at utility scale is that they'll take your excess slack in these module whips and they'll skip over the next module over and just go every other module, which allows them to, not just skip over the modules, but then come back. What you do in and they're able to do that because utility scale panels are a little bit taller than residential panels. And so these cable whips are a little bit longer than residential panels. So residential panels that are shorter with the shorter cable whips, you just don't have enough length in your cable whips to do this. And so what you end up doing is, when you're plugging into your next door neighbor in a portrait orientation, you end up having a lot of extra slack. And then you have to build a home run cable to get you back home. And that extra slack and that home run cable results in slightly more efficiency loss, slightly more voltage drop, slightly more material cost, slightly more stuff to do, slightly more labor cost. So, I put this slide in a few years ago to think about, that's just kind of interesting. And then a few years later, I'm up on the roof thinking, what do I do about all this extra surplus cable on the roof that I need to manage? And the answer was, maybe I can't skip over them, but I still can twist that cable around to get rid of the slack. Let's see. Got a few more slides, so we'll take our break at a quarter till, just like we did last time. When you're doing an off-grid array, it is common to do a ground mount, and it is common to have a house with trees, like a house in a forest that's next to an open field. And so you're going to want to have your ground mount not in the shade. You're going to want to have your ground mount in the open field. And so the question is, well, how far away can you get your array from your house? And the answer is, as far as you want. It's just a matter of cost. The further away you go, the thicker your cable needs to be because of voltage drop. You're going to lose efficiency as you travel. And so the other aspect is when you look inside of a cable jacket, so here's our outer jacket, and then here is our copper that's inside our cable. Voltage has more to do with the toughness of the jacket, and amperage has more to do with the thickness of the cable. And so solar cable is rated for 2,000 volts. It's rated for utility scale application. Even though at residential you're staying down with 600 volts, the cable itself is rated for very high voltage. And so what the Solar Edge system does, as we mentioned before, it will increase the voltage and it'll decrease the amperage. And what that means is you can get more power through the same gauge of cable. And so when you're going over very long distances, it is cost effective to increase the voltage. And that's why when you come out of a power plant, they step up the voltage to incredibly high, tens of thousands of volts, to transmit it over long distance power lines before stepping it back down to lower voltage in your home. So we can apply the same concept when your ground mount is long distance to say you want to have this home run be high voltage. And so that's where you might choose a 600 volt charge controller instead of a 150 volt charge controller. That's where you might want to choose a 600 volt DC home run instead of running this back at 240 volts AC. You want high voltage when transmitting over long distances. And so that's where the Solar Edge system, which steps the voltage up to the top of its range, is very useful in an off-grid setting, because if you're doing a ground mount that's far away, you want to get that voltage up. And solar, there's utility scale products that will step up the voltage to 1,000 volts or 1,500 volts or 2,000 volts, but then you would need to step it back down because there really aren't, 1,500 volt residential inverters or 1,500 volt charge controllers for that matter. But there are 600 volt charge controllers, and Solar Edge gives you a DC home run that steps you up to very high voltage. The problem is Solar Edge says you can't use us for off-grid. And on top of that, Solar Edge has those rinky-dink lithium-ion battery inverters that only power critical load panels and not your whole house. So that's not the end of the story. We're going to come back to that in the last section of class. So we talked about tracking. I'm not a big fan of double axis trackers. There are companies out there that make them, but the foundation work on double axis tracking is a lot more expensive because now you're supporting, 15 panels on a single post instead of 1 or 2 panels per post going down a line. And also, I think the aesthetics of double axis tracking are kind of like the aesthetics of these big satellite dishes, which were really cool when they first came out, but over time became an eyesore. I think double axis tracking, being a big, giant rectangular plate, is an eyesore as well. Whereas I think single axis tracking at a residential job site would be more like a fence than anything else. It's low to the ground. Midday when the panels are flat, you can see over the top. Do you really need tracking for off-grid? Probably not. Again, with off-grid, you're going to have stranded energy anyway. And so maybe your battery will get fuller a little bit earlier in the morning, but you're supposed to be filling up that battery anyway. Maybe you won't, maybe you'll be running off solar a little bit more on into the evening, but the sun's still going to set, so you're still going to need to be running off your battery anyway. And so maybe that's another reason why we don't see a lot of residential tracking, is that maybe tracking is better for grid-tied systems when you have something to do with every single kilowatt hour that comes out of the array, whereas off-grid, you have that stranded energy as a function of good design. As we said on this slide, so we're just going to keep going. And so, I've actually kind of designed my own residential tracker to kind of test this out. There is some added cost. It's not that much more, which is why utility scale does it. You get more production in the morning and evening. We've talked about these points, so these are just kind of reiterating what we've already discussed. So what we did is we bought some bearings. We actually got a square pillow block bearing so we could put some square steel tube into it. And we just, had made sure that we were using a laser level on our pipe caps and putting the pillow block bearing on the pipe caps. We found an actuator with enough juice in a control board. And, at the end of the day, the material cost really was rather negligible. We were building a $25,000 project, and we basically were able to convert it into a tracking array for about $2,000 more of material cost. And, if the tracking doesn't work, it still produces energy. It's not, it's not like when the tracking functionality, if it, there wasn't much risk involved. I put a picture in. I must have made this slide before we did the pictures. The main problem with the tracking array is that it's just, it was just a little bit more of a hassle to install. It just took longer to install and get up and get working than to just do a fixed in place array. So ultimately, as a solar installer, I'll make more money off doing fixed in place arrays rather than trying to be progressive and engineer my own racking system for tracking. And so, if you're up for the challenge, do it yourselfer challenge, then you want to be a little bit different. I would encourage you to say that you can do tracking and have it be as cost effective as a fixed in place array, if not a little bit more cost effective, but you're still going to be a pioneer. So what we were looking at is about a 11% increase in our project cost to go from fixed in place to tracking. And tracking will give you, and you can use PV watts to run the simulation, but, tracking will give you 15 to 20% more power out of the array. And so the incremental cost increase is smaller than the additional power gain. Ergo, tracking is cost effective, which is why tracking dominates the utility scale market. And while the same argument can be applied to the residential market, it just doesn't have any interest from manufacturers and installers. Maybe there's a market opportunity there, but maybe it's a small enough market that nobody cares about it. The main kind of thing that I think people should be aware of is that there are generators that are being branded or marketed as renewable generators. And so it would make sense to assume that a renewable generator that is being marketed for off-grid living, off-grid use, is what you would want with your off-grid solar array and battery array. Generac says it's the first one warranted for off-grid use, used in parallel with an alternative energy system. Okay. Well, what does this really mean? Well, for one, a renewable generator may have a auto start controller that can be triggered based off a battery voltage state of charge. But guess what? Your battery inverters have these auto start generators too, and you only need one of them. You don't need two of them. And it's probably better for the battery inverter to control when the generator turns on and off rather than the generator to determine when it turns on and off. So that the systems don't get confused. Generac is assuming that an off-grid generator is being used regularly. But remember, we're designing our system so that the generator does not need to be used regularly. So this renewable generator has a larger oil tank so that you don't need to change the oil so often. The generator has a resonator to mute the sound of the generator because presumably you're using it a lot. You don't want to have to listen to it, so that it has a quieter mode of operation. Well, neither are particularly applicable to a true backup generator that is not being used on a daily basis. This Generac renewable generator is kind of assuming that you're going to be using it at night and running off solar during the day, so that you're going to be using it very frequently. Here's another one, is that the generator has a more expensive alternator. So there's that concept of dirty electricity, which is not good for your electronics, where the frequency is jumping around as the generator surges from a lower mode of operation to a higher mode of operation. And obviously, if you're running your building off of a generator full time, you want a very clean signal. But if you're just using the generator to charge your batteries, the battery inverter is providing the clean signal already. And so the question is, do you really need the quieter resonator and the bigger fuel tank and the auto start controller and the higher end alternator? Or do you just need a regular generator to turn on once in a while to charge the batteries back up and be done with it? And the answer is the latter. A generator that will surge up and down as a function of your electrical load is going to be more efficient than one that, doesn't have such advanced throttling. But again, remember, our generator is there just to charge the batteries. So, renewable generators are high quality, but they're really not necessary for you to purchase. What is perhaps more important is a generator that will, be capable of auto starting with your auto start controller, A, and then B, one that's, sized so that, it can recharge the batteries so you can switch back over to your battery inverter as quickly as possible. So a true backup generator does not need to be a high-end generator. A true backup generator you're not using frequently. Now, I did this calculation, basically by connecting the dots on these charts. But I'm not trying to portray myself as a generator expert. And I did get one audience comment last time I taught this class that he felt that I was being too aggressive on the calculations. But what I was looking at is running, a natural gas or a propane generator. And this is just a regular generator. And it gives me, how much gas it uses per hour of operation running at 25% of the load, 50% of the load, 75% of the load, or 100% of the load. So that was another thing, is that, generators don't just run at their listed output capacity. Even a standard generator can throttle up and down a bit. So we said, okay, well, let's look at a 25 kilowatt gas generator running at 25% of its load for 24 hours. So if you're running, off a generator all day long because it's a cloudy day and your battery bank is not large enough, looking at the burn rate of the generator at 25% of its load and the cost of gas or the cost of propane, what we conclude is that it is cheaper to run off the levelized cost of solar plus the levelized cost of your flooded lead acid batteries as opposed to a gas or propane generator. And we're assuming that a gasoline generator is even more expensive. And so that's where we get into the conclusion that, you really want to just keep buying more batteries until, most of the days of the year, you do not need to rely on your generator to operate, that you can get through the night on your battery bank and then have the battery bank recover with solar. Or that you can get through, if you're finding that it is common for you to go 3 days with clouds and then the sun comes back up, you want 3 days of storage and then the sun comes back up. The generator only being there for weather anomalies, like a hurricane comes through and there's clouds in the sky for a week solid. You run that generator halfway through the interim to make sure your batteries don't fully discharge. And so again, remember, we're just running our generator to protect our batteries from the deepest state of discharge. And so we ran our generator back here. We'd have to run it on this day, and then we'd have to run it on that day. But then we would get back into a period where our sunny days are recovering the deep discharge from our batteries. And we're examining our load so that, by increasing our battery bank by just that much, we're avoiding two times in this, 3-month cycle. Normally during this, we'd have to run the generator once, twice, 3 times, 4 times, 5 times, 6 times, and then we'd likely recover. Well, by going from a 90 kilowatt hour battery bank up to a 122 kilowatt hour battery bank, instead of running the generator 6 times, we'd only need to run it 4 times. So by increasing our battery bank by 30%, we reduce our reliance on the generators by 35%. At the same time, going any further than that, increasing our batteries by another 30%, well, we would still run into these instances where we would need to run the generator, so that wouldn't do us any good. So there is a right sizing for battery banks, your solar production, and your backup gas generator, which I hone in on through modeling the building the model in Excel, and then just running a couple of different system sizes, a really large solar array on a really small battery bank, a small solar array on a really large battery bank, mid-sized solar array on a mid-sized battery bank, and just toggling the different components until we run into, what optimizes our generator runtime. You can also think about different kinds of heating resources, because the system is most strained in the winter time. And so you could say, okay, well, maybe I don't want to do electric heat. Maybe I want to have, gas heat or wood chip heat. Just keep in mind that even in the wintertime, you're going to have periods of sunny days. So even though you might be running off wood chip heat for half of the winter, on those sunny days in the winter, you could still run off electric heat and be fine. And so we're talking, by doing your model, you can look at, okay, well, I'd be spending $600 less on gas a year if I go from a 90 kilowatt hour battery bank to a 120 kilowatt hour battery bank. And that incremental difference for the battery bank would cost me an additional $6,000, which would mean that by upsizing my battery bank to 120 kilowatt hours, I would get a 10-year payback. And if my off-grid system has a 12-year payback, and I can get a 10-year payback by increasing the size of my battery bank compared to my cost of running the gas generator, then generally that's going to be an acceptable buy for the client. What is more interesting to me is the discussion of what size of a generator do you need? Do you need a small generator or a large generator? Generally, I would say you would want a large generator. But the problem as we get into our circuit diagrams is we'll see that the current from the generator circulates through the inverter system. And so you don't want to press 20 kilowatts of power through a circuit that's only rated for 10 kilowatts. And so, generally speaking, you don't want a generator that is grossly oversized compared to your renewable system unless it has its own, overcurrent charger where you're isolating the solar components when you're recharging the battery with your gas generator. And so that would say you got to be cautious about oversizing your generator so that you don't burn up your terminal lugs when forcing that power to circulate through the system. So where would that come into play? Like why would you have where could you have a really large generator and have that work out even if your solar array is kind of small? You might not even have the generator recharge the batteries. A very simple setup would have a transfer switch between your solar battery and your generator and have it be either or. Because, running the generator to recharge the batteries and then to run off the batteries, that's a strategy. A different strategy would be just to run off the generator until the sun comes back up to recharge the batteries and then switch back over to your batteries. So, if you go for that higher end renewable generator, then you might keep them isolated from each other. And then you would get a whole house generator for whole house power. And so if you have a small solar array, but you want the capability to have more power than what the system can provide for when you're having big events like Thanksgiving or New Year's, then you might go for a large renewable generator and run off the generator power during your heavy load events and then run off the solar array and then switch over to your solar array during the non-heavy load events. And then, the few times a year where, the solar array battery doesn't do good enough, switch back over to the generator and just wait for the sun to come back up and ignore the issue of wiring the generator to the solar battery entirely. Keep it simple. Or you could go with a smaller generator that is integrated to recharge the batteries. The problem with, I guess I've learned some new things since I made these slides. The problem with large versus small generators is really an issue between stationary generators, which tend to be large, and portable generators, which tend to be small. And the problem with portable generators is that they rarely have the ability to auto start. So I'm going to pull up an example to kind of better illustrate this point. Let's go on to good old Google. I'm going to Google for a portable generator with electric start. That kind of sounds like it's what we need. Okay, well, here's a very popular, quality portable generator. And it's being marketed as here's one. Here's a quality portable generator, and it's being marketed as having an electric start. All right. But what they really mean is that this generator has a little push button on it where you go and you press it and it starts up. Instead of like a pull crank that you crank. Well, okay, but how do you wire the auto start module on your battery inverter to this little electric start push button? Well, the answer is you gotta take your screwdriver and pry that button off and find the wires and get out a solder gun and solder some connections onto that electric start button, and hopefully you know what you're doing. I mean, just because it has an electric start doesn't mean it has a auto start wiring capability. Whereas your portable generators will typically have terminals for the auto start. In fact, I've looked far and wide for a generator, a portable generator with an auto start, after figuring out that what is kind of the standard configuration is for the portable generator to simply bypass your batteries and inverters and power the home until your solar array charges the batteries back up. And the way that you would then charge the batteries is you might have another AC circuit that has a battery charger on the AC circuit, so that when the generator is charging the home, you have a separate circuit that's charging the batteries independent of the solar inverter itself. It's a little confusing. But again, that's because if you have a 14 kilowatt battery inverter and you have a 20 kilowatt generator, you can't circulate that generator power through the inverter, or you'll burn up the inverter terminals. And so there's this Ames is not a company that I would strongly recommend. They're kind of a low end, very cheap inverter company. And so what I mean by that is, like, the Chinese battery inverters are made to go inside in an air-conditioned, dust-free environment, whereas the most popular battery inverters on the American market are rugged, made to go outside, and also more expensive. So there is an element of you get what you pay for. But what I think is really neat about Ames is that they've come out with a generator. So let's go look at their 6 kilowatt generator. And let's see if I can find it real quick. Look, over here, right here, they actually have a landing terminal for a 2-wire electric start. And so they've actually come out with their own generator, portable generator, to have an auto start where you don't have to hack the button. And it took a solar inverter manufacturer to come up with their own portable generator to have this functionality. Otherwise you get into large stationary generators to have these kinds of terminals for an auto start module. Well, why is that? Well, it's not necessarily a good idea to have a portable generator hardwired to an auto start, because what that means is it's not a portable generator. It's a stationary generator. And so, I think that electrical inspectors and code boards would rather you see a hardwired permanent generator actually be a stationary generator rather than a portable generator, is kind of my thought on that. I have a solar installer friend who really specializes just in off-grid, and he says, I don't like the auto starts, because if the client's, running out of power, I like them to know what's going on. The idea of the system just running on its own, hands-free, could get someone into trouble if they're, really need the power but they haven't realized their generator's been clicking on and off, and all of a sudden they're out of gas when they really need it. So another consideration with off-grid on how automated you want the system to be. And so really what you want is either a large generator with a separate AC charger for the batteries tied into your electric service panel, or this particular Ames portable generator, which is small enough to be, circulating the power through your, standard battery inverters without burning up the terminals. I don't know, too many other options. And we'll talk about this a little bit more as we get into our one-line diagram discussion. So let's look at some wiring diagrams and see if we can't figure out how these things get wired up and how they work. Now, this is kind of a simplified one-line diagram. It's not really a wiring diagram. It's just something to kind of tell you what's going on. Where here's the grid, and that's tied into the AC, and then there's a separate output for a critical load panel, and then here's the DC terminals for the batteries. And if this is a bidirectional inverter, the inverter can outflow as well as inflow. And then some, this is a Schneider one. It's a bidirectional. Some single directional one-way inverters will just have a grid input and then only output to the service panel. This is more of a proper wiring diagram. So let's kind of talk about what's going on here. Let's start with our solar array. And remember, our solar array has variable voltage. And so we run it and wire it to our charge controller to fix that voltage down to our 48-volt battery bank. So it'll take our 600 volts from our solar array and bring it down to 48 volts to our battery bank. Well, here we don't just have one solar array on one charge controller. We have a larger system. We have 2 solar arrays and 2 charge controllers. You might have 4 charge controllers, or if you're using 150 volt charge controllers, you might have 8 charge controllers. So eventually all these charge controllers have to be wired to your single battery bank, or maybe you have 2 strings of battery banks. And so what we see in this wiring diagram is the DC output from the array landing here. The DC output from the array landing here. And then this one is going to the charge controller. And this one here is going to the charge controller. And so we have these individual breakers for the charge controllers. And where they're coming out is this other breaker, which is which is wired up to the DC side of the inverter. And so what we have is at this section is our solar arrays landing on breakers and then coming out to our charge controller. So that's our 600 volt bus. And then we have separate breakers that are for the output of the charge controller. Here's the input. Now we have our separate breaker for the output of the charge controller. That is, one side is for 600 volts, and then that's going into the charge controller. And then coming out of the charge controller is still a DC circuit, but it's for our 48 volts. And that's where we have our 48 volt battery. And we have multiple terminal lugs here. And so this is where we would be lugging on multiple strings, and notice how this particular Schneider unit with this particular bus bar, it has terminals for 1, 2, 3 strings of batteries. And Schneider says, you know, you don't want to have more than 3 strings of batteries. You're going to have a bad time if you do. Well, then we have slots for breakers. And look how these breakers are a lot larger than these other DC breakers. Remember, this is the 600 volt side, so we're at high voltage and low amperage. This is the 48 volt side, so we're at low voltage and high amperage. And that's why these breakers are so much bigger than these breakers. And so here are high amperage DC breakers that are running into the DC input of our inverter. You know, then we get to our inverter output circuits. So our inverter is converting from DC to AC. And so now we're getting into our inverter output circuits, and we have some inverter output circuits landing over here. We have other inverter circuits landing over here. So now we have this side, and now we have that side. And then we have this one in the middle. I guess that's coming up here. Let's see if we trace them all around. This one's coming up and then landing on the top here. So we have an inverter circuit on the bottom, an inverter circuit on the bottom, and an inverter circuit on the top. You can't really see what these letters say yet. Let's see if we can just figure it out. Then we have our generator, and it's coming in and landing on the top here. And then that's what's coming down and passing through our inverter so that this generator can charge these batteries and then coming back out. And that's where we're saying is if the generator is being used to charge the batteries through the inverter, then the generator and the inverter have to be the same size. Otherwise, you're going to force too much power through these inverter terminals and burn them up. And so that would be to say, oh, you need a small, kind of portable generator because a large stationary generator is going to be too big. And if you want to use a large stationary generator, well, then you want to have it being isolated from the inverters, even if you have a separate charger from the AC service panel still running back to the batteries independently. All right, so we got our generator cycling through our inverter and coming back out. And then we got one of the inverter circuits is landing here, the other inverter circuit's landing here. Well, here's our grid connection. And so our grid's coming up at the top. This is our inverter output for the grid tie. This is a bidirectional inverter. It's interconnected to the electric grid right here and feeding the grid. And then we have the other circuit that comes in from the grid and goes and runs this service panel right here. Well, look, this is being fed from the grid, and here's our grid interconnection, and this is being fed from the grid, and it's also being fed from the inverters on their own breaker. This is where the inverters have a transfer switch that when the grid goes out, it isolates the grid connection and then powers the critical load panel. And so what we see is a whole bunch of AC breakers for grid interconnection, for critical load panels, for backfeeding the grid, for accepting a generator charge. And then we also have DC bus bars that are quite big and thick because they have high amperage and low voltage versus low voltage and high amperage, or high voltage and low amperage. And these wiring diagrams are found in the inverter manuals. Now, the inverter companies want to make it real easy on you to design a system using their products. At the same time, if you're not buying the expensive specialty combiner panel, but trying to buy a box and piece this stuff together yourself, it becomes a lot more complicated because you get bus bars that may be rated for high amperage but aren't rated for high voltage. Generally it becomes less quality of a build when you're not using the specialty combiner panels that the stackable inverter companies sell. So that can be a hidden cost. Schneider's specialty combiner panel costs over $1,000 plus the breakers. Outback's only costs about $500. It's a little bit better of a deal. So on my next one, on my current job, I built my own combiner panel out of lower cost components. I wasn't very happy with the level of professionalism of my own job on that one. But I was using a Schneider system and I didn't want to spend $1,000 on, a service panel. The next time I'm going to go use Outback's, even if I still use Schneider's products, I'm going to go use Outback's service panel. When I'm designing the permit document, I'm not giving them the final wiring diagram. I'm giving them something a little bit more simple, like this one-line diagram, but with a little bit more detail. And with batteryless solar, it's very easy to, just go online, get the sizing software, figure out how many, if you have, 25 modules, figure out how many circuits you have and how many modules are going to be on each circuit. And then I use a software called Solar Design Tool to generate my one-line diagrams for me. And the reason why I like Solar Design Tool is that this whole image right here is computer generated. So they connect all the design features of National Electric Code, your voltage, your amperage, your overcurrent protection, your wire size, your conduit size. And not only do they put it together on a really nice report, but they give you a one-line diagram generator, which is actually better than, Solar Design Tool is a cheaper software compared to the more name brand solar design softwares like Aurora Solar or Helioscope. But in this particular application, it is more functional because Aurora Solar and Helioscope, they're not trying to do your electrical design for you. They'll give you a one-line diagram, but they're not going to present it in a way that you can just print it out and give it to your permit office, whereas Solar Design Tool is really trying to be a permit package software. Well, the problem or the joy of off-grid design is, all this software that's been automated for batteryless solar is not programmed yet. So you're getting back into having to, pull open NEC, do your own design calculations, and generate your one-line diagrams on your own. And so what I'll do is I'll start the design in Solar Design Tool, and it gives you kind of the pictures shown. And then what I'll have to do from here, what this is showing is my solar circuits and my inverter and my disconnect and my interconnection, but it's not showing the battery and it's not showing the charge controllers. And so what I'll have to do at this point is export it into CAD and then finish out the design, the old school way, doing your own voltage and amperage calculations and adding the rest of the system in CAD. So I'll use Solar Design Tool to do the non-battery components and then export it to CAD and finish up the drawing in CAD, doing more of a custom design. So that's kind of nice about off-grid solar, is it gets you back into doing custom designs and custom hourly work, whereas batteryless solar has become so automated that it can get a little boring. These are just some screenshots from Solar Design Tool, but in the interest of time, it puts together conduit sizing, calculations. I just include this slide to give you an idea of different system components and costs. This is for a non-battery system, so let's just keep going. I think I got rid of the smart home stuff in this presentation in the interest of time, but let's see if I can't just briefly comment on it. I don't know. Let me see what's in your handout. Let me scroll down real fast. Let's see. Well, sometimes in my handouts, I like to put in a whole bunch of information. It doesn't quite always fit into a nice 6-hour package. But given that I'm just now installing my first smart home, I might have a few things to say on it. All right. So off-grid and smart homes go together really well in ways that are not really being addressed by smart home devices yet. So what I mean by that is like the Nest thermostat. Sure, it can control your air conditioning by an app, but really what we want is a thermostat that will throttle the air conditioning based on our battery state of charge. If our battery is very healthy, we want our air conditioner to crank. But if our battery is getting low, we want our thermostat to kind of, go up a degree or two and not run our air conditioning so hard. Your battery inverters have relays that you can program and set for various use cases. And so, like, here's a relay on the Schneider inverter, and you can set that relay to activate some kind of auxiliary output based on low battery voltage or high battery voltage, or low battery temperature or high battery temperature. And so it's possible to, have an air conditioning unit and say, okay, if I am at a full battery, turn on the air conditioner, turn on the dehumidifier, make some water, make some distilled water so I don't have to go get it. If the batteries get cold, turn on a heating element. So that's kind of interesting. Although the relays are limited, you kind of get to choose one thing for it to do. Now, here's a thermostat. And thermostats have similar relays where it's like, okay, you know, prioritize when you want to use electrical heat or when you want to use gas heat. You know, as a standard kind of multifunctional thermostat choice. Depending on what, you know, if you want to use electrical heat as auxiliary heating or as your standard heating. You know, so it's like a heat pump is a good example. Heat pumps are very efficient, but they don't work when it gets so cold outside. And so that's when you might turn on your gas heater instead of using your heat pump as a standard thermostat setting. So what we really want is our thermostat to talk to our solar array. Well, how do we do that? You know, especially if we only have very limited relays within the battery inverter itself. You know, because it's really not just the thermostats, it's the ceiling fans. You know, if our battery's at a healthy state of charge, we want our ceiling fans to be able to turn on. But then if our air conditioner clicks on, we want to be able to turn our ceiling fans off until the surge load of the compressor drops down. And then we want our ceiling fans to, you know, turn back on again. And if we can do all that, instead of having an electric load that jumps up and down, we'll have an electric load that's perfectly flat. And if we have an electric load that's perfectly flat, then we'll be achieving, you know, a discharge rate on our batteries that's more like a C20 discharge rate instead of a C5 or a C2 discharge rate. You know, so we got a lot of electrical devices in this house. We got air conditioning units, we got refrigerators, we got freezers, we got ceiling fans, and not all of those devices need to operate at the same time. You could turn off the deep freeze when the air conditioner clicks on and have no quality of life difference for the tenant. The air conditioner clicks on, the deep freeze can sit without functioning for an hour or two and coast off the thermal mass inside the deep freeze and then turn back on again later without the food, you know, thawing. So how do we actually do the smart home? How do we actually get all these devices to work together? There's a home automation bandwidth that's called Z-Wave. This says the Z stick. It's a Z-Wave. Well, what is the Z-Wave? The Z-Wave is not Wi-Fi. You know, Wi-Fi takes a lot of electricity. You know, those Nest thermostats need to be powered by the wall. You know, they have batteries in them, but that's so that if the power goes out, the thermostats don't lose all their settings. And then if, you know, hopefully the power turns back on again before the, you know, batteries wear out. But you go on Twitter and you Google, you know, my Nest thermostat, I have to change the batteries every 2 weeks. And there's a lot of people out there complaining that the batteries in their Nest thermostats seem to only work for 2 weeks. And that's because they're running their Wi-Fi thermostat off batteries only, and it takes a lot of juice to run Wi-Fi antennas. Z-Wave is the same bandwidth that old school cordless home telephones used. So if you remember, you had your wired telephones, and then all of a sudden, you had home telephones that were wireless but they could only get about 20 feet from the receiver. And then a few years later, a second generation of wireless telephones came out that you could get all the way across the other side of your house and still talk on your cordless phone. That's the same thing as Z-Wave. It is a low energy, long range bandwidth that you can't transmit like videos or pictures or Wi-Fi over, but you can transmit communication signals on and off. And because it's a low energy bandwidth, it can also go through walls a lot better. And so there's a platform called Z-Wave, and then there's another platform called Home Assistant, which is open source. It's produced by Google. And there's a community based around low energy computers, an example being the Raspberry Pi. You take the Raspberry Pi, you plug in a Z-Wave antenna, and you install Home Assistant, and all of a sudden you have a home automation network, for under $100 that can communicate with other Z-Wave devices in your home. So what are some Z-Wave devices? Well, here's a Z-Wave device that's a 40 amp switch. Here's a Z-Wave device that is an energy meter that goes inside your electric service panel and that will measure the energy that your building is using. And so you use Home Assistant to program the code between your meter inside your service panel and your electric switch that turns your heavy-duty devices on and off. And so in our automated smart home, we have an electric hot tub. But the electric hot tub cannot work at the same time as the air conditioner. And so if they're in the hot tub and the air conditioner clicks on, we turn the hot tub off until the air conditioner drops down. So if they're hitting, we use the smart meter so that when they're hitting the maximum output capacity of their inverter, we turn off some luxury heavy-duty devices so that they can still operate within the parameters of their inverter and their off-grid system. A different kind of wireless platform is remote-controlled cars. That's that first generation of cordless telephones. And there's buttons, electric switches that you can turn on and off with radio frequencies. And, again, with the Raspberry Pi, you can connect RF antennas to it and program the Raspberry Pi to turn your RF switches on and off, although it doesn't work quite so well as Z-Wave. Sometimes the communications on the RF stuff get a little confused. And so between your Z-Wave thermostat and your Z-Wave energy controller, you can say, okay, when I'm getting up to 15 kilowatts of power, turn my thermostat up to 75. And then when I drop down to 5 kilowatts of power, turn the thermostat back down to 68. And so by integrating Home Assistant and Z-Wave devices, you can start using your smart home as a function of its power draw. So we're testing this stuff out right now. We're building the house for it. I finally got the internet up and running so that we're broadcasting the house over our internet. And by the end of the week, we're building a custom computer for this house and actually implementing some of these concepts that we've talked about in class really for years. And I'm trying to think of some of the Z-Wave stuff that we're doing. We have Z-Wave door locks, Z-Wave garage door openers, so that the when the client gets home, the garage doors open and the doors unlock. We have Z-Wave smoke alarms, which really, do you need a smart smoke alarm? Well, what's interesting is they cost about the same as a regular smoke alarm, maybe $10 more. But, if they do go off, you can see which one's going off. You can check the battery state of charge of your smoke alarms on your phone. And then perhaps most importantly, it just acts as a repeater for your Z-Wave network. So the more Z-Wave devices you put inside your home, the stronger and faster your Z-Wave network becomes. There's Z-Wave light switches, which are really interesting because if you have Z-Wave light bulbs, then you don't actually need light switches on your homes anymore. There's Z-Wave sensors that sense light and motion and temperature and humidity, which is really interesting because if your smoke alarm is telling you what the temperature of the room is, you really don't need a thermostat on the wall anymore. You just need a air conditioner that can plug into Home Assistant. Door sensors that'll tell you if the door's open and close. Window sensors. Our alarm system is a Z-Wave system so that all of our sensors can now communicate with the alarm system. The doorbell. I really want a Z-Wave mailbox so I can know when the mail arrives, but haven't seen one of those yet. So let's kind of take that thought and we're going to apply it to a concept that I call Frankensolar, which is where we're piecing together a solar array bit by bit, where we start out with like a grid tied subsidized solar array with net metering, but then down the road the net metering policies go away and we want to convert to off grid, but we don't want to throw out the baby with the bathwater. We want to select our devices so that they all feed into each other, and we want to achieve some double redundancy so that when the power goes out, when one part of the system fails, the whole system doesn't go offline. We still have some backup power. But at the same time, we don't want to just buy two of everything either, because that's not very cost effective. We want all of our different system components to play unique roles without the whole system going down when one part fails. So we're going to start out with one of the most popular inverter systems on the market, which is SolarEdge. And SolarEdge is not rated for off-grid. It says SolarEdge can be installed with a generator, but it cannot operate at the same time as a generator. If you do, it'll void your warranty. Well, okay, you could put that on a Z-Wave switch. You can land your I'm back in my presentation. You could land your SolarEdge inverter on one of those 40 amp Z-Wave switches and program Home Assistant to digitally turn off the SolarEdge array when your generator's working. So that gets rid of you needing to have a physical interlock switch for that. So SolarEdge says we don't like you to combine your production with a generator. What Schneider says in comparison, this is the Schneider product, it says, well, you can combine, it says do not couple inverters, regular solar inverters, batteryless solar inverters with our battery inverter unless you have a game plan. Unless you have a way to dump excess power. And so that could be a Z-Wave device that's like a water fountain that turns on when your Z-Wave energy meter records that you have a surplus amount of power. And so, like, here's a battery inverter saying that you can connect the battery inverter with anybody else's batteryless solar array. But we have SolarEdge saying we're a batteryless solar array, but you cannot connect us with anybody else's battery inverter. No surprise, SolarEdge sells their own battery inverter, which you can connect to. You know, they want to keep you within their ecosystem. Yes, in the interest of time, these are some more Schneider functions. You know, an auxiliary relay, we've talked about that. You know, a transfer switch that'll protect the critical load panel. You know, we already talked about that. We haven't really talked about equalization charges. Equalization is when your batteries are already full. You know, I talked about the battery voltage chart kind of looking like that and said this is when your batteries are full. Equalization, this is voltage and state of charge. When your batteries are already full and you apply more current to them, their voltage will still crank up. And as soon as that charging current goes away, the voltage is going to drop right back down again. So equalization is when your batteries are already full, but you apply additional power to it to crank that voltage up. And that's used to bust those barnacles off of the anode. It's just a maintenance charge, so I guess it's kind of off topic. And so here we have a system where we have our SolarEdge DC optimizers, which are necessary for fire protection provisions in National Electric Code. And SolarEdge is one of the only companies that make these DC optimizers. There's like 2 or 3 more. And so it's National Electric Code is almost mandating that you use like the SolarEdge product on their, you know, on rooftops. But SolarEdge doesn't make a whole house battery inverter. It only makes a lithium-ion battery inverter that can protect a critical load. And so if you're living off grid and you want to have a code compliant house and you have a shaded roof, there's really no reason not to use the SolarEdge system. Or if you have a ground mount and you're at high voltage for far away ground mounts, there's really not a reason to use the SolarEdge system except for the fact that they don't have a good solution for whole house off grid. Now, they do have a great lithium-ion battery inverter. And while lithium-ion batteries are too costly to run the entire house off-grid, one thing you can do with lithium-ion battery inverters is program them to only turn on when your power is above a certain threshold. So use them for demand management for spiky loads rather than for base loads. Well, lithium-ion or lead-acid batteries are terrible for spiky loads, but they're great for base loads. So what you would really want to do is have a system that has both a lithium-ion battery and a lead-acid battery so that you're mostly running off of lead-acid, but through digital controls and a demand management inverter, you can have the lithium ion take over your spiky loads, and that'll allow your lead acid to stay at its C20 discharge rate, and the lithium ion can take over those spiky loads. You know, our house that's off grid, we're like pressing the maximum output capacity of what our 15 kilowatt battery inverter can do. And so, you know, right now our solution is we actually have two service panels. And so the solution is we're just running the battery inverter to one service panel. So we're having one service panel off grid and the other service panel on grid. But the plan is to, as the price of lithium ion drops, we'll go ahead and at that time add AC coupled lithium ion batteries in demand management mode so that they're really there to power the heavy load startup surges, like when both of the air conditioners click on at the same time. You know, the SolarEdge inverter is a grid-tied inverter. It's capable of backflowing onto the grid. Our all-in-one cheapo Ames inverter is not rated for grid connection. It's a one-way inverter that cannot connect to the grid. And so maybe I'm already grid-tied and I have a SolarEdge inverter and I want to sell back to the grid. Well, what would I do then? Well, I could still have my Ames inverter and put it on a generator interlock switch. You know, the main problem is I want to connect I want to use my solar array to charge up my flooded lead acid battery, and SolarEdge says, we're not going to let you. You know, you're running this 600 volt circuit down from the rooftop, and I have a 600 volt charge controller, and I have a 600 volt inverter, and I want both my charge controller and my inverter to share that 600 volt home run. That way I can charge up my lead acid batteries so that when there's a blackout, I can go and flip the interlock switch and turn my system on, and then reprogram my SolarEdge inverter not to be a master inverter, the regular inverter, but instead reprogram it to demand management mode so that I can run my whole house off grid and AC couple a grid tied inverter to a battery inverter without them having to really communicate with each other, without having them needing to be the same manufacturer. And then at the same time, if something goes wrong with my battery inverter, I still have the critical loads backed up by my lithium ion inverter. And there's a value in that too. The SolarEdge says, you know, so basically what we want to do is share our DC home run from the array, be able to use the proprietary DC optimizers that help you meet National Electric Code rapid shutdown, and they pretty much have a monopoly on the DC optimizer market. It's not a completely, but there's really only one other company that makes DC optimizers, and then there's one other company that puts inverters up on the rooftop, and it's almost the same thing, but not quite. So even though SolarEdge says you can't do this, what would happen if you tapped on a 600 volt charge controller onto that 600 volt bus? Well, I called SolarEdge and asked them that, and they said, you're not allowed to do that. It could possibly turn the system off. Oh, well, what does that mean? Well, I went and I looked at inside the SolarEdge technical manual, and I see that, you know, basically what it does is it adjusts the voltage so that the home run circuit always has a constant voltage no matter how many of the optimizers are functioning. But then, and all this stuff, in the interest of time, I'm going to skip some of the technical detail. So what I found in their manual, it says, oh, we have a couple of questions. What's the normal expected lifetime of industrial flooded lead acid? They're rated for 3,000 cycles at an 80% depth of discharge. And so in normal off-grid settings where you have 2 or 3 days of lead acid capacity, most days you're going down to a 30% depth of discharge, which would mean that effectively they could last, about 9,000 days. And so you're a well-sized lead acid system that you condition and take care of can last for 20 years. Oh yeah, and Gary, you said try remote start on the generator. It's like the same thing. It's an electric start, but you still have to bust open the remote to wire it to the auto start module. And so in the SolarEdge documentation, I skipped ahead a couple of slides, but in the SolarEdge documentation, I finally found a clue. It said the minimum string length is 6 panels for this optimizer or 8 panels for that optimizer, and the maximum is 25 panels onto a given circuit. And then likewise, it says completely shaded modules could temporarily cause the power optimizers to shut down, but as long as you have a minimum number of unshaded power optimizers in the string, it'll keep functioning. And so in other words, what they're saying is if your charge controller draws enough power out of this circuit that doesn't make it to the SolarEdge inverter, the SolarEdge inverter will turn off, just as if the modules were completely shaded. So drawing power out of the DC bus and redirecting it for other uses is the same thing as not having that power there to begin with, which is the same thing as having a shaded solar array that's not producing any power. And so the takeaway is, if this is a 4.8 kilowatt charge controller, then we have to say, well, maybe I have to have, 25 panels on a string. Because if my minimum string length is 6 optimizers, and I'm getting 300 watts per optimizer, that's 1.8 kilowatts is the minimum amount of power the SolarEdge circuit needs to operate. And the maximum amount of power is 7.5 kilowatts. And so I subtract the two, and I can draw as much as 5.7 kilowatts of power out of that DC home run before the SolarEdge circuit turns off. So in fact, I can combine and this is just all the math to optimize it, but we're getting near the end. And so the fact remains is that I can in fact tap a 600 volt charge controller onto the same DC home run as my optimizer lithium-ion battery inverter and have it work. And so in this kind of system, what's neat about it is you could start out with a grid-tied SolarEdge system. And you actually don't even need to buy the lithium-ion battery yet. So I have a client where we went ahead and upgraded him to the lithium-ion battery-capable SolarEdge inverter, and he's grid-tied, and he sells back to the grid. But his long-term plan is to go off-grid. But really, he just wants some backup power. So we're just biding our time And then eventually we're going to add, when the price of lithium ion batteries drops, we're going to go ahead and add a lithium ion battery to them. But then he might say, okay, well, now I want to do another step further. I want whole house power during a blackout. And so at that point, we would add a flooded lead acid battery bank on, all-in-one battery inverter, and then put it on a generator interlock switch. And this kind of system, you could run a separate AC charger to it, or we could go ahead and add a charge controller. And the reason is, once he gets this far, he could cut the grid entirely, and if his Solar Edge inverter fails, he can still draw off that 600 volt to charge the lead acid battery. And if the lead acid battery fails, he can still have critical load backup capability until we fix his, incredibly dirt cheap Chinese battery inverter. And so what we've done is we've kind of achieved some double redundancy where we have two inverters, one for handling peak loads and the other for handling base loads on two different battery chemistries, even though neither manufacturer will tell you that they support multiple battery chemistries. But multiple battery chemistries is what's needed to really unlock the value of living off grid, where you have your cheaper batteries providing your base load and your more expensive batteries managing your peak load. And so that's what the rest of the program kind of summarizes. So I've kind of wrapped that up in your notes. And gone through different configurations where, you could have a batteryless solar array with a backup generator on an interlock switch, and then later, expand your system by adding various components to go off grid on your own terms. And then lastly, budgets. That's important. I'm not going to read them out to you, but you have them there for future reference.